Uh, Coordinator Madam, is there any update regarding joining of our group CEO, sir? Or Prosenjit, sir, is there any updates that whether he would be joining?
No update to me. Soma madam is trying.
Okay, okay. I think CEO sir has joined.
Yes, he had joined.
So kindly make him a co-host or okay.
Hello, am I audible?
Yes, yes, sir. Yes, sir. You're perfectly audible, sir.
Okay, okay. You
Okay.
give me signal when should I start talking?
Yes, sir. So we actually were waiting for you, as you have
Okay,
already joined. So we will start now, sir.
okay. Uh,
Ashwin, please start the program.
Okay, okay,
okay.
okay, okay. A very good
Uh,
evening.
as
Our speaker
I'm
has already arrived.
okay.
Pushpin, please start. Suvamoy sir has already joined the meeting.
Yes, yes, yes.
Okay. I'm extremely sorry for not being able to join yesterday's inaugural program. That was exclusively the technical problem. Even today I was facing. I'm sorry. I extremely thankful to all the faculty members and especially the convener of this ATAL FDP program. With lot of efforts, they have arranged the best of speakers, and I'm extremely hopeful that the faculty members who have joined yesterday and will be continuing the total program will be highly benefited. I have gone through the schedule and the topics very much apt, very much to the topical, and at the same time industry oriented and skills oriented. Today is the second day. Time is very short. I wish you all the best to Dr. Shoma Bandyopadhyay, Dr. Shubroto Thakur, and all the other faculty members and all the participants, those who are joining today's talk and for the coming future talks. I congratulate each one of you to take the bold decision to participate actively. I know my voice may not be audible because I am on the wayside and just standing on the roadside and speaking. My wish always be with you for all the best for the nation and for the future humankind. Thank you.
Thank you very much, sir. Thank you. So, participants, good evening, all of you. So, you are already being welcomed by our Group Chief Executive Officer, Professor Dr. Partho Sarathy Chakraborty. Sir has already told that he was unable to join yesterday's inaugural session due to some technical issues. So, on behalf of the organizing committee, we feel very honored that due to his busy schedule and overcoming all sort of technical problems, sir has finally joined with us. We are very happy, sir, for your presence. Thank you, sir. Thank you very much. Okay. So, with your permission, shall we, sir, move on to our first technical session? So, let us now move on to our first
Yes,
technical
yes,
session.
yes,
Yes.
Pushpin, just
Okay.
start.
So,
Sir has already
we are
joined.
okay. So, we are truly honored to have with us a distinguished expert from NIT Durgapur who has contributed immensely to various fields of computer science. Today, he will be sharing thought provoking insights on quantum computing, a quantum jump toward sustainable computation. Though we are connected virtually, let us all extend a warm welcome to Dr. Suvamoy Changder as Sir joins us in this session. On behalf of the organizing committee of our 6 days online ATAL faculty development program on quantum age intelligence, I welcome you, sir, in this gathering. Dr. Shubhamay Chongdar received his PhD in Computer Science and Engineering from National Institute of Technology, Durgapur, India in 2011. Currently, he is an associate professor having 24 years of teaching experience in the Department of Computer Science and Engineering at NIT Durgapur, West Bengal, India. His area of research is quantum computing, information security, steganography, watermarking, and computational aesthetics. He has presented his papers in several international conferences at USA, China, Egypt, Malaysia, and also our own country, India. He has published 68 research papers in reputed journals and international conferences. His Google Scholar citation is more than 850 with H index 16 and I10 index 28. He has served as a technical program committee member in several conferences and also served as reviewer of several renowned journals, including IEEE Transactions. He has served as a resource person in several workshops, invited lectures, training and learning programs. He has presented several sessions on quantum computing, data security, steganography, machine learning, deep learning, and even wildlife photography. So let us again welcome you, sir, in this virtual gathering. Now over to you, sir. Dr. Changder, please.
Thank you. Am I audible?
Yes, sir, you are properly audible.
Okay. So now onwards, I will switch off my video just to show my face to the audience. I keep my videos on, but I think it will be better to off the video and go
Just
to.
we will keep a snapshot, sir.
Oh,
We
okay.
will take a snapshot.
Okay, okay. And I think the video will create a little bit of disturbance for data transfer, so that is it is better to off. Again, during the question answer session, if there, then I can on the video.
Absolutely, sir. No issue.
Okay, okay. So before starting, just to introduce my topic, this is a very basics of quantum mechanics and quantum computing, because whatever I thought, since we are learning this topic, this is a topic, very new topic to India. Not very new, but towards us it is very new, and since all of us are learning the topic, so I thought, not going to the details of my research area about quantum image representation and processing all this, because it may become very boring to all of you. So I thought to discuss a very interesting and basic topic like teleportations, and also what is the requirement of quantum computing nowadays. So that I will discuss. So anytime if you feel bored, so raise your hands or say, sir, please stop, I'll stop. Okay. Anyway. So let me share this one. No? Okay. So I need a little bit of time. Is it visible? This
Yes, sir.
quantum?
Absolutely. It is clearly visible.
Okay, okay, okay. I think there is some problem, right? Okay. Right. So already you are aware about the topic. The topic is quantum computing. Cannot do this. Okay. Can you help anyone that how to hide this? Okay. So quantum computing, a quantum jump towards sustainable computation. So that is the topic. So here I prefer to start the any of the presentation or on quantum computing with this great statement made by Niels Bohr that everything we consider real is made of things that cannot be regarded as real. So I don't know that how many of us believes on this, because there is a very distinct difference between the classical physics and the or real physics and the quantum physics. So here lies the problem, or we should not say the problem, the philosophy is different. So all of us are created or are made of with electrons. But if we go on with the lectures and the slideshow, then you will find that the electrons are not behaving like us. But we are made of by electrons, but electrons are not behaving like us. So that's why Niels Bohr, the greatest, one of the greatest scientists, he said that everything we consider real is made of things that cannot be regarded as real. So let us move. Now, what is science? If we consider that what is science, then we can think about that science, we say science if and only if when we go for some experiment in a condition, and if we repeat the experiment in the same condition, every time we will get the same output. That is the science. So if we have a fever, always we take or consume the paracetamol of some power. We do not take any antacid to decrease the fever. That is science. But here we are having an experiment that a photon beam is coming on this simple glass bottle half filled with water. The photon is coming, and after hitting this area, the photon is just getting inside the bottle, and there is a liquid, maybe water. Some of the photons are getting inside the water, and you can check it that some photons are just reflected. So some are refracted and some are reflected. That is very, very fine, because all of we are aware about the angles of incident and all these, right? But the question is that when the photon is coming through here, can we say that which photon is going for refraction and which photon will go for reflection? All the photons are same, are carrying the same properties, but after getting here, some are getting refracted, some of the photons are getting reflected. But before that, before hitting this, we cannot conclude or say anything about by watching the property of the photon that which is going to be happen now. So is it not a science? But the scientists started to think about that, what is going on, why we are not getting the answer for some of the questions that is being watched in the nature. So next is this. Here we are having a platform, lots of holes are there, small holes are there here, okay? So whenever the lights are getting bombarded here, so we must get some holes here, just here. But instead of getting holes, what we are watching, we are getting a line of lights. What is going on? Now, if the photons, if the photon is a particle, we must get some holes of lights here, okay? But instead of that, we are getting lines. So all of we are aware that since photons and electrons all are behaving dual property, sometimes it becomes particles, sometimes it becomes waves. That all of you are very much aware, and that's why it is going on. So there is a very popular experiment which is known as double slit experiments. All of we are aware about that, so I'm not going to discuss the details on that. But here one electron beam is there and double slit screen is there. So if the electron or the photon is passed through this double slit, instead of getting two slits here, we get a series of slits. The middle one is very with higher intensity, and the sides are little lower, and all these. That is also very fine. So here, whenever we are watching this, it is a particle. Whenever we are not watching this, it is moving like an wave. All of we are aware. But the question is that if we put an observer here, that means suppose we are having one camera which can detect whether the electron is passing through the slits or not. If we keep a camera here to watch the electron, immediately you will not get these slits, only two slits will be there. Interesting. So someone may say that due to some gravitational fields and other, because quantum gravitation is one of the booming area nowadays, that may happen. Okay. So it is disturbing the electron, that's why it is passing either through this or through this. So we are getting two slits only. Anyway, if we put an observer or the camera here in between the screen where the photons are or electrons are getting collected and this double slit screen, what will happen? Again we will get two slits. That is also fine. That after going through this, some disturbance is there, that's why we are getting two. The interesting thing is that if we put a camera here at the end or after the screen, what will happen? Then also we will get two slits. So now the question is that how electrons or the photons are thinking or getting the view that someone or something is watching us. That is the question. So here lies the measurement property of the light particles. So the thing is that till we do not measure a light particle, it behaves like an wave. But whenever we insert a measurement device or apply any measurement device, immediately the wave becomes particle. And here in quantum computing, we will use this dual property or dual nature property of the light particles. So just for our interest, some other experiments were made by some of the researchers. So here you see that how mathematics also fails to define and to describe these phenomena that is going on in the nature. So this is a photon source of photon, and this is beam splitter. Beam splitter means if we send this photon here, beam splitter will send the photon either through this path or through this path. And these two are the detector, photon detector. So beam splitter will slit or shift the source photon to either this path or this path. So according to the mathematics, this is the mirror, this is the mirror. So it will get reflected here and it will go here. If it select this path, so it will be reflected here and this path. So as per the mathematics, the chances of getting a photon here in D1 is 50%. The chances of photon getting detected here is also 50%. So probability is half. That is fine. There is no problem. But let us check this. Here again, we are doing the same experiment. Here we are sending the photon through this direction. It is a beam splitter. So it will split the photon to either this or this. There is a mirror. There is also a mirror. Now, from the previous one, we have just changed one thing, that here we have inserted another beam splitter. So which will split the coming photon either through this direction or through this direction. So let the photon is coming through here. Maybe the beam splitter is sending to this. It is coming through this path. This beam splitter either will send the photon here and here. So as per the law of or the rule of mathematics, again the chances of detecting the photon here in detector 1 is half, and here also half the probability, right? But interestingly, if we send the photon through this direction, and in this experiment, always the photon will be detected in detector 1. It will never go to detector 2. Similarly, if we send the photon through this direction, always it will be detected in detector 2, not in detector 1. So mathematics fails here. Now what is going on? So these are very, very interesting things that the researcher got interested in quantum mechanics because of this. But the actual idea or the concept came from the photoelectric effect. All of we are aware about the solar electricity. So whenever the photon is coming to a particular metal, some electron is getting ejected. So if two photons are getting here, bombard here, two electrons, three, then three. So we can say that if n electrons are getting photons, then n electron will be ejected. But no, the photoelectric effect can be shown that for after a certain value of n, it will not increase, it will be decreased. So then it was derived, and some constant, all of you are aware that Max Planck has given one constant, and by which we can easily explain all these. So from there, the quantum concept of quantum came, and people went for all these experiments, and they found that yes, all these are going on where the real mathematics, the classical physics, all are becoming fails to explain what is going on. And after that, two groups of scientists, one led by great Einstein and another led by great Niels Bohr, they were really believing in different concepts. So Einstein wasted his last 30 years to prove that quantum concept is false, but he was genius. So to prove the concept is false, he has given lot of things which was helpful for the quantum people. So anyway, that is a concept that how this classical physics and the quantum physics differs, but all of the things are nurtured by the nature. Okay. So similarly, one very popular and which is the needs of everything for the life being is photosynthesis. So how photosynthesis occurs? All of we know that the photon from the sunlight just bombard on the leaf, and some chlorophylls, with the chlorophylls the leaf of the tree prepare our foods, right? But no, that is not so simple. Here actually, when a photon is getting bombarded along with the chlorophyll, one particle extra exciton is being formed, right? And the whole leaf is not the kitchen of the tree. On the leaf there is a particular space, few particular spaces are there which are known as the kitchen of the leaf. Now the problem is that we have to move this excitation, not we, actually the nature is doing. Exciton should be moved to the reaction center or the kitchen of the leaf. That is very fine. But the thing is that how this extra exciton will find the proper path, because photon is having limited energy, it is decaying. So if exciton or the photon has to find the proper path, that is optimized path, first it has to find the paths. Lot of different paths are there, and among these the optimum has to be found. So do you think that the photon is having that much of time to find the optimal path? No. So we can say that some of the time this extra exciton will reach to the reaction center and we will get the food, and some of the time it may miss. But contrary to this concept, it has been found that nearly 100%, not nearly 100% of the time, the exciton reaches to the reaction center without any delay. Without any delay. The question is that how exciton find the optimum path to reach the reaction center, right? So here, if we believe that photons and electrons are behaving like ghosts. That means whenever we are not watching, it is behaving like smoke or wave type of thing. That it at the same time it is watching the whole leaf, right? Now, whenever it has found that one reaction center is there, and reaction center is a measurement operator. So if reaction center finds that okay, something is there, so then this wave is becoming particle and reaches to the reaction center without finding the optimal path. If this excitant is looking at the same time to all the paths and find the optimum one, okay, without any calculation and others, just like an wave that is spreaded over whole leaves, and whenever it found the reaction center, it becomes a particle and prepared the food. If it happens, then we can justify the 100% nearly or not nearly 100% accurate food preparing concept. Okay. Similarly, there is another big question: how migratory birds find their exact paths. So there is a theory of magnetism. Magnetic theory is there, that small or tiny magnet is on the inside the eye of the bird, and we are having a big or huge magnet in the center of the earth, and we can say that these two magnets are finding the direction of the bird. But is it believable that a very tiny, very small magnet can interact with the magnet that is residing in the center of the earth, and it is nearly 5,500 if we consider 11,000 kilometer diameter of the earth, 5,500 kilometer down from the surface of the earth, and these migratory birds are flew not less than 5,000 above the, not less than, it is much higher, even 10,000 kilometer away above from the. So is it possible that a tiny magnet can interact with another magnet with 10,000 kilometer away? Some researchers are trying to find this theory, and some researchers says that no, it is not that much of believable. Now they given another concept, which is like old film of Judua Bhai, or twin brothers sisters, that two brothers and sisters went for to watch the Mela, and they get separated. Someone is just uh, living in a village, and someone is living in a city, and they very much apart from each other. But if someone is getting heated by some person, then another uh, gives some reaction. So let us believe in this type of story. Now think about, there are two particles, one is in the eye of the bird and another in is the nature, maybe in the earth. Okay. And they are interacting with each other without having any communication media. Let for the time being we believe in this theory. That means if I disturb one particle, another particle will automatically be disturbed, and there is no requirement of any kind of medium. If this theory is believable, then we can justify that how migratory birds find their exact path. Because if they change the direction, there will be a disturbance in the particle that is reside in the eye of the bird, and automatically that particle which is reside in the nature, maybe on the surface of the earth or anywhere in this universe, will be disturbed. So by these two disturbances, they can find out that something is going on wrong, and they can change the birds can change the direction. If we believe in this theorem, then it can be justified. Now the question is that, are these theories believable? So here today I'll try to show that yes, it is possible that without having any communication medium, we can transfer the information. That is, two electrons, two photons can interact with each other without having any communication media. Okay. So that is known as teleportation. But before that, another interesting area is that how electron moves and what is the position of an electron inside an atom. There is no proper answer. These are the chances that in an atom, the electrons may reside in these black areas. There is a chance this area. Now see, the position or the chances of getting an electron inside an atom are different in different times. So we cannot say anything about the position of an electron, that in which orbit it is now, whether it is in zero state or in one state. So it is just like something like wave or ghostly, and that's why Einstein told that I don't believe in all these ghostly things. Nature do not play dice with us. So these are the sentences uttered by greatest scientist Einstein, who did not believe in all these theories. So we are the very simple and normal persons. Yes, it is very tough to believe, but these are going on in the laboratory nowadays. Nowadays, people has invented the method to teleport the information from one space to another place without having any medium. Okay, and these are going on. So today we'll go for discussing this, that how it can be done. Okay, right. So this is the thought experiments made by, all of you are aware, Schrodinger cat. Schrodinger cat. Here I'm not going to explain that what is going on here. So this is a black box, or it is a closed box. Inside one cat was there, and it was being asked that what is the status of cat after a few times, that if there is some radioactive substance, some poison is there, so what will be the status of the cat. So in real life we say that either cat will be alive or the cat will be dead, but in quantum we say that cat in both the state alive and dead. At the same time, cat is alive and dead if we do not observe. Now, if we open the box, then we will find that either cat is alive or dead. But if we do not open the box, then the status or the state of the cat is alive and dead, which is the big difference, or it is a great, the concept is different than the real life. In real life, in real physics, classical physics, we say that cat is either alive or dead, but in quantum we will say that cat is alive and dead. And okay, so there lies the concept, and we will use this concept in our quantum computing. Now, why we need quantum computing? So some may think that it is a parallel computing, but it is not a parallel computing. In parallel computing, we need some parallel computing systems, but here in quantum, we do not need any parallel computing system. Why? Because you see the inherent parallelism. In our classical computing, what we do, we are having some gates. So these gates are open, then one. If gates are closed, then zero, or the vice versa, anything. So the operator, all the operators that we operate, either we will operate on 0 or on 1. That is classical computing. Okay. But here you see the quantum concept is that at the same time 0 and 1 exist at the same time, and 0 and 1. So if we find some operator that will operate on 0 and 1 at the same time, then what will happen? We are having, say, either 0 or 1, that is 1 bit. So in classical computing, by using 0 or 1, we use 1 bit, or we can operate on 1 bit. But in quantum, what we do, we are operating 0 and 1 at the same time. So 2 to the power 1. Now think about, if we are having a n bit string, then in classical computing, we can operate on n bit only. But in quantum, we can operate on 2 to the power n. So now just think about that all the exponential time complexity algorithm will become polynomial time algorithm if we apply quantum computing, and if we have really in our hand the quantum computers. Then all the exponential time complexity algorithms will be converted to polynomial time algorithm. So inherent parallelism are there in quantum computing. Then what will happen? So the property that I have said of these twin brothers and sisters in quantum, that property is known as entanglement property, and this exists. Believe me, this exists. After this lecture, you can just Google it and you can check it that how entanglement is going on, or we can prepare the entangled electrons and entangled photon inside the physics laboratory. You can check it, okay? And these are going on using no cloning property. There is a very interesting property of these smaller particles in quantum computing, that is no cloning. You cannot copy any state. Here in classical, whenever we are sending some, say one email, so what we do generally, we are writing a mail, we are sending to the receiver. So at the same time, one copy is with me and one copy is with the receiver. So that is meaning of cloning or copying, okay? So in classical computing, copy is possible, but in quantum copy, you cannot copy a general state. Any arbitrary state cannot be copied. So what will be the usefulness of that? So suppose we want to send a state or any information from one to another, and some hackers is trying to hack this. So that means that hackers is trying to make a copy of the state. So whenever that hackers will try to make a copy of the state, immediately the whole system will be destroyed. So no one will having any copy with anyone. Therefore, the security system will be much more powerful, 100% safe. Okay. So with the quantum computing, the data will be secured with 100%. But in another side, all the things are having the opposite side. So whenever we will get the quantum computers, by applying source factorization algorithm, we can find the primary factors of any number in polynomial time. Now, can you imagine what will happen? All the cryptographic system, that is the password system of your debit card, credit card, emails, everything will be vanished within a second, right? So that is another challenge. But quantum cryptography is taking the lead to replace the classical cryptography system. So if someday the quantum computers are available to all of us, then the things will be changed. Okay. Similarly, during the search in an unstructured database, in a structured database, we can find, we can search any elements, maybe in the best case order of 1. Okay. But in an unstructured database, so the time complexity is order of n. Now think about the data size. Nowadays we are using the Facebook, Instagram, Amazon, the big sorts, all these, they are using lot of data. And if we have to search an element within this bunch of data, so the time complexity is very, very high. It is polynomial, obviously order of n, but n is too large. By applying quantum computing, Grover's, okay, lovely Grover's, he is an Indian. So he developed a search algorithm which will find any item in an unstructured database with the time complexity order of root of n, which is very, very less than order of n, okay, order of root n. So these are the usefulness of quantum computing. So now, how it will help to make our computing system sustainable, that is the main issue. Okay, because our topic is to check that how to make this sustainable computing and all these. Okay, so now even this computing system, you know, this IT industry, a supercomputer to run a supercomputer, the electricity that we need is the total consumption of a electricity of a small town. Can you imagine? So if we can replace the supercomputer by quantum computer, so how much electricity we can save? And obviously, if we do not use the energy too much, the computational power and the computing system will be much more sustainable. All the IT companies that are using the electricity, information technology in 2020, they are using 11% of the global electricity consumption. Can you imagine that how many computers are running? So 11% of the global electricity consumption are there for IT industry only. That is also 2020. Now 5 years elapsed. It has been changed, maybe maybe 13% or 14%. So here, since a quantum computer can solve problems in few hours, which supercomputer may take, just think about, several tens of billions of years that can be solved by quantum computer in a few hours. So obviously the electricity consumption and all other energies will be much less, and that can leads us to the sustainable society and computing. Okay, so here just one example, one Google's quantum processor consume only 26 kilowatts, which is far less than a supercomputer, and runs a test of quantum algorithm. These are all are being possible now. But here, so someone may ask that then why should not, whenever we'll get the quantum computer, so all these classical computer will be replaced by quantum? No. So here lies the crossing point. Okay, so if the computing requirement is very less, then we should go for classical computing. But if the computing power is too high, then we should go for quantum computer, because quantum computer will be much costlier than the classical computer. Okay, so there lies the breaking point. So when to use which one? But by using quantum computers, easily we can find that the energy consumption will be much less, and it will be much more effective and helpful towards the human society. Okay, so now as I told that I will try to discuss that the teleportation system, that means how we can transfer informations from one place to another place without having any communication medium. So before going to that, all of you are aware, I know, I believe, still just for a recapitulation, I'm discussing these few points. That to represent a state, we need Hilbert space, which is a complex vector space with inner product. Why we need inner product? Because to make our set or the space finite, if we do not impose this condition that vector space with inner product, so if we make a product of two vectors, the space will grow increasing and increasing. So since inner product is within this space, so therefore if you multiply any two vectors, that is, multiply means if you take the inner product of any two vectors, the output must also be within that space. So it is a finite space. Okay, so Paul Dirac, he has suggested one new notations to represent quantum states. Actually it is linear algebra, he has not given for quantum state, but we are using. So two familiar notations are there. One is Kate, which is represented as this, and another is bra. So actually if we have two vectors, one vectors maybe this, say one Kate vector is like A and B, that is AIB, which is equivalent to A plus IB, and this is represented this. Then the bra vector which is represented this is generally is A minus IB. Okay, so it is the conjugate transpose, so it will be row vector A B but with minus I, and this is AIB. So this is the representation, nothing else, simple. Just we represent another algebra, this is the representation. Inner product and outer product, all of us are aware, so we are not, I am not going to this. What is basis vector? Basis vector is the combination of vectors by which we can create any vector within the space. Orthogonal, inner product 0, orthogonal to each other if there are vectors. And if we normalize, that is, if we take the value of that, it must be unit. So if we normalize the vector, just like say 1 by root 2 alpha plus 1 by root 2 beta, and these are the amplitudes. If we take 1 by root 2 square plus 1 by root 2 square, so it will become 1 normalized. So this 1 by root 2 alpha plus 1 by root 2 beta are known as orthonormal vector, and if these are the basis vectors, then it will be known as orthonormal basis vector. Now, how to represent a quantum system? Actually, we are considering in quantum computing three basis vector. One is x vector, x basis, y basis, and z basis. I will explain. So among these, z basis is very helpful and effective, which is known as CBS, computational basis vector. So without going to this, let us try to understand that how it can be represented by using block sphere. This is known as block sphere, because first we have to visualize the thing. After that, we can go for computing and all these. So here, any state can be represented by this three-dimensional space. Okay, this one is z. Z is represented by up z is 0 and down z is 1. Actually, these are the concept of how electron spins. Actually, we are considering the electron spins in three different ways, which is not true. Electron can spin in any form. People do not know that how electron spins. Sometimes it may spin upward, sometimes it may spin downward, sometimes it may with an angle and all this. We are considering three different spin. One is up, another is down, and another is mid. Okay. So up spin is represented by 0, which is z axis. Down is 1, which is minus z. One is x axis. Here you see the x axis is represented by 0 plus 1 by root 2. Here lies the concept of superposition state. See, this is a state which is AND of 0 and 1. AND of 0 and 1. That is, at the same time, 0 and 1 exist. Okay. This is known as superposition state, and this represented by the x-axis of the block sphere. Similarly, we are having another superposition state. You see 0 minus I1, 0 plus I1. That is another superposition state, which is also known as y-axis. Okay. Here this x-axis, y-axis, and z-axis, they are perpendicular each other, and we consider these three are orthonormal basis vector of block sphere. So whatever the state or vector we will represent in quantum system, quantum computing, all the states will be represented either by z-axis or by x-axis or by y-axis. We will not consider any other vectors here. Okay. For other purpose, you can represent, there is no limitations. But for quantum computing, we will use these three basis vectors. The concept is something different, that why these type of things are there, why x is, just like see that z is 0 and this z is 1. So now someone is here and he or she is trying to watch the both end. What will happen? He or she will not be able to watch 0 particularly or 1 particularly. So he or she will get half of the 0 and half of the 1, though not half and 1. Okay, half of 0 and half of 1. Just he or she will get a state which is a collection of 0 and 1. Okay, maybe 50-50 chance from here. This position maybe 50-50 chance. If you change the position, you will get some other probabilities. Okay. So that's it. That is known as the superposition state. That means instead of getting a particular state, two states are being superimposed with each other. That is known as superposition state. Okay. So here there are representation of the gate. You see that 0 in the block sphere, 0 is represented as gate 0, and this is nothing but the vector 1 0. Here lies the difference between quantum computing and the classical computing. In the classical computing, 0 means 0. There is no other question. Okay, no doubt. But here quantum says that yes, 0 means probability 1 that is 0 with probability 1 and 1 with probability 0. Instead of saying 0 equals to 0, 0 is 0, we say that a quantum state 0 means the 0 is with probability 1 and 1 is with probability 0, which is same, but the concept is different. We are representing a state with more than 2 bits or qubits. Okay. Similarly, 1 is represented with, you see, 0 with probability 0, 1 with probability 1. That is the main difference of classical computing and quantum computing. If we understand this one, all the things will be easy. Okay. And these two are represented in this form. Here you see this is 0, this is 1. Okay. Right. So we can provide some now the thing is that, you see, all of you are aware that some axioms are there in quantum mechanics, right? So after defining the states, that how to represent the next thing is that if we apply some operator, how the things will be changed. That is the axiom 2. Okay. Then in axiom 3 we go for measurement. So here you see, if we give a rotation, say I am here, I am watching 0, and suddenly I am rotating this x in this direction. Okay. What will happen? The person who is watching something here, that person will move here. Or if we say that the state 0 was there, and if we make a rotation, if we give a rotation here in this axis, so this 0 will come here. What is this 0? This notation is 0 plus I1, right? 0 plus I1 by root 2. So that means if we apply a rotation, an operator, the states are getting changed. So it depends upon the angle of the rotations. Here we have given 90 degree. Similarly, we can give 180, then 270, then 360, and so on. So depending upon the rotations, we can change the shift, and we can go for different kinds of operations like the classical computing. As like in the classical computing, we use NOT gate, OR gate, AND gate. Here also we are having different kinds of gates, and we can apply, right? Anyway, and all these can be represented theoretically by using block sphere. So these are the preliminaries I have already discussed, right? Now you see the superposition state is represented as alpha 0 plus beta 1, such that alpha square plus beta square equals to 1. Why? Because we have already discussed that it must be normalized. So if we take the values, it must be equals to 1. And superposition state means at the same time we are having both the state. So what is alpha? Alpha, actually it is known as probability amplitude, and if we take the square of these values, it gives us the probability. What does it mean? It means that suppose this is a state which is a superposition state, that means 0 and 1 at the same time both exist. Now in the classical computing, both 0 and 1 does not exist, and we reside in the classical world. So finally, whatever the output we will get, that must be classical. Now the thing is that this is a quantum state, this is a superposition state. We are applying some operators and all these, but finally we have to get some classical output, and that can be done by measurement. Okay. So whenever we will measure this state, we will get either alpha square or we will get beta square. So we say that we have received the state 0 with the probability alpha square. We have received 1 with the probability beta square, in this way. So finally, whenever we will go for measurement, just try to recollect that we said these light particles behave like wave if we do not watch this or measure this. Whenever we will go for measuring this, it becomes particle. So here lies the same concept. This is like wave, the superposition state. It is not having any particular value, but whenever we are measuring the value, either it will collapse to 0 or it will collapse to 1, but after measurement. So that is classical. Okay. Right. Next, in normalized superposition state, I have already given the example anyway. There is a very interesting gate, Hadamard gate. If we apply Hadamard gate, this state, zero state, which is known as pure state, will be in the superposition state, 0 plus 1. And this 1, if we apply this, it will become 0 minus 1. So just giving you one example of an operator, just like OR gate, AND gate, we are having Hadamard gate. We are having quantum NOT gate, all these. Okay. So Hadamard gate is a very popular gate by applying which any pure state can be converted to its superposition state. Okay. So some gates and others are there like operator or C NOT gate, which is known as control NOT gate, is it flip the target bit if the control bit is 1. Okay. Similarly, we can represent more than one qubit. So here 0 and 1 represent single qubit. 0 is a single qubit, 1 is a single qubit. But we can represent two qubit system, which is 0 0 means 1 0 0 0. 0 1 is this, 1 0 is this, 1 1 is this. Similarly, you can take 0 0 0 0 1 1 and all these. Okay, 2 to the power 3, this cubic system. This is known as quantum no cloning theory, but I will not explain this. Mathematically, it can be proved that you cannot copy or you cannot make a clone of any state, any quantum state. Okay, then it will be destroyed. So mathematically, it can be proved, but since we are having limitations of time, so I am not going to prove this mathematically, but all these are truth. Okay, these are believable. Quantum entanglement inseparable. Inseparable means, just for an example, you see here, it is a state. Now, actually, before going to quantum, all these mathematics and others, the history of quantum is very interesting. John Bell, a scientist who believes in the experimental results. There are two types of researcher in this world. One is theoretical, who believes in pen and paper, and they are doing tremendous job. And some of them are experimental researcher who do not believe in pen and papers. They go to the laboratory and do it by themselves and check the result. So actually, John Bell was also trying to disprove the quantum theories, that no, it does not exist. All these are fakes. There may be something ghostly and something hidden which we do not understand. So let us go for finding in the laboratory. So John Bell went to the laboratory, and what he found, that yes, there are few states, maybe for photons or electrons, where these are inseparable, means we can create two electrons. Suppose this electrons is spinning upward, this electron is spinning upward, and these two are entangled with each other. Entangled means, if you take this far apart and if you change the spinning of this electron from upward to downward, automatically it will be downwards. It will be disturbed in this 0 0 0 and 1 state. If you prepare two electrons in this form, and if you disturb this electron, okay, from 0 to 1, automatically this electron will be changed, disturbed. Similarly here and here, John Bell has checked and found that these are going on. So these are the four most entangled states, which are known as Bell states. And believe me, all these can be prepared in the laboratory of the physics. We can create the electrons and photons which are inseparable. That means if you disturb one, automatically another will be disturbed, and they do not have any communication with each other. Okay, these are going on. So here are some more some famous interesting gates, like Pauli's X gate, which is known as quantum NOT gate. If you apply to 0, it will be changed to 1. If you apply it to 1, it will be sent to 0. Oh, sorry, 1. Similarly, Pauli's Z gate, it is used for phase change. Similarly, Y gate, this is also required to change the actually wave is being shifted towards plus or minus. Tensor product, all of you are aware. If we take the tensor product of these two, we will get all the combinations of 0 and 1 like this. Okay, tensor product, not the combinations, actually it is a product. Now you will find another term which is known as oracle. Oracle, nothing but black box having some operator or operators. So if we say that we have the states is passed through the oracle, that means this state is passing through some operators, and some operations are going on this state. Okay, so these are the basic terms. So here, unlike classical computer, measurement in quantum computer gives one of the many possible outputs with a certain probability. That already I have told you. But there is another concept, that is probabilistic computing. But again, quantum computing is not a probabilistic computing. Probabilistic computing is something different, where we are aware about the numbers, the probabilities, and all these. But in quantum, we are unaware, completely unaware about the output. We will get the output only when we are measuring this. So probabilistic computing is not at all a quantum computing. Okay. So I am not going to prove the no cloning theorem, though it is here. Right. So just I have another 20-25 minutes. So how? Just a minute, huh? Director sir is calling me.
Okay, sir. No issue.
এই আমি একটা এতে আছি গো, তোমার অনলাইন মিটিং এ আছি, মানে লেকচার দিচ্ছি। 7:30টার সময় ফ্রি হলে থাকবো যদি স্যার থাকেন। একটু বলে দাও, অনলাইন মিটিং বাইরের ইনস্টিটিউট আছে। ওকে, ठीक है। हाँ हाँ हाँ, आते हैं सर, आते हैं। ठीक। Sorry, am I audible now?
Yes, sir. You're
Yes, sir.
properly audible.
Okay, very sorry.
No, sir. It's
Okay.
okay.
So teleportation means we want to transfer some information from one point to another without having any communication medium that is traveled continuously between 2 points. So just keep this in your mind, that is it possible in classical computing that if we want to say any wrong information, even suppose I want to send A through email, but somehow B is reached to the receiver without having any communication medium, it is not possible. Okay, so why I have told this, just after a few minutes you will be able to find that why. But the interesting point is that in quantum computing it is possible, though it is wrong information, but information can be passed from one place to another place without traveling or traversing or sending or whatever you say, any medium, through any medium. Okay, so here let Alice and Bob, two person, they want to share one state. Okay, one state. Let a superposition state, any common state alpha 0 plus beta 1, that Alice want to share with Bob. Just like our classical computing, let I want to share A with any one of you. Okay, so what we do, we just convert it to the binary and send it through mail or WhatsApp message or mobile or anything, by any digital means. So here Alice want to transfer or share this alpha 0 plus beta 1, which is a huge amount of data. Just think about, alpha can be any value in this world, beta can be any values in this world. Since this is the probabilities, it must be between 0 and 1, but this is also infinite. So this alpha 0 plus beta 1 is an infinite, is a huge volume of data, which is quite impossible to transfer by using classical computing. Number one. Number two, here by using quantum, you will find that we will not require any communication medium. So what they did, they actually prepared to say electrons, okay, entangled electrons, fully entangled electrons, Bell state. Okay, Bell state. So let both will either move up, that is spin up, or will spin down. And Alice and Bob got separated in two different places. Maybe Alice is in Earth and Bob is in Moon. Okay, they do not have any communication, nothing, no. Alice can do some operations on the bit of Alice. Bob can do the operations on the Bob's bit. But Alice cannot do anything on Bob's bit. Bob cannot do on the Alice bit. Why? Because they do not have any communication. Any communication media is not there. So Alice's operator will not be operatable on B and Bob's, and similarly the vice versa. No one can do anything on the other's bits. Okay. Now Alice want to transfer alpha 0 to beta 1 from say Earth to Moon late. Okay. How? So here already we have discussed that let Alice and Bob shares the Bell's first entangled bit 0011. It means these two are with, this is the state of the Alice bit and this is the state of the Bob's bit. So if Alice electron is spinning up, Bob's electron will also spin up. If Alice electron is spinning down, Bob's electron will also spinning down. That is the interpretation of this 00 and 11. Okay. And let Alice want to transfer this alpha 0 plus beta 1 to Bob. So what happens? Alice is having one laboratory, Bob is having another laboratory. They do not have any communication media. So Alice is containing one of the electron among these two, and Bob is containing one of the electron among these two electrons, and Alice is having this state which she wants to share with Bob, and they do not have any communication media. So what is going on? I have just given or represented these red color bits are for Alice and the blue colors are for the Bobs, and they got separated. They are entangled, but they are separated with a distance. Inseparable is something different, and separated with distance means they are getting separated in a distance, but the properties are inseparable. Okay, if you disturb one, another will automatically be disturbed. Now what will happen? They are preparing a circuit. Okay, so this psi is nothing but alpha 0 plus beta 1 which Alice want to transfer, and Bell state all of we have studied that 00 plus 11. This is the Bell state. So these are the inputs to the system. Now whenever we are giving these two inputs, actually it is going through tensor product. Okay, so it will be tensor. You see that 000 will be multiplied, then you will get 011, then 100 and 111. So we will get this state alpha 000, alpha 011, 100, 111. Then what is going on? This is the C naught gate. C naught gate means if the first Q bit or first bit is 1, then the second Q bit will be flipped. If it is 0, it will be 1. If it is 1, it will be 0, something like that. So just check what is going on. Here it was 0, 0, 0. So there is no change. Okay. Then 0, 1, 1. First bit is 0. So there is no change. Here the first bit is 1. Second bit is 0. Here you see that since the first bit was 1, the second bit is changed from 0 to 1. Since this is quantum C naught, control not gate. Here also first Q bit is 1. You see the second Q bit is changed to 0. So after applying this C naught gate, we are getting the state. These three electrons are behaving like this. Okay. Right. So this is flipped. These two flipped due to the C naught gate. Then what we did, we had applied the Hadamard gate on the first qubit. So here this qubits will be changed. And we have already said that if we apply Hadamard on 0, it will be 1 by root 2 0 plus 1 and 1 by root 2 0 minus 1, something like that. So what will happen? If we apply this Hadamard gate, we will get this type of equation. I will supply the PDF of this. Okay, don't worry. So later you can also check that how it is going on. Simply this 0 is becoming this, 0 is becoming this, 1 is becoming this, and 1 is becoming this. So what is going on? You see, this is the Alice part. Okay. Something wrong is there. Please wait. Right. So Alice can operate on these two bits because it is with Alice, and these blue colored bits are with Bob. So you see that Alice cannot do anything on blue bits. So blue bits are remaining same. It was 0, it was 1, it is 0, it is 0. So all these are remaining same. There is no change. But Alice has operated the Hyderabad gate, so it becomes this. Now just we are rewriting in this form. You see, if we take these 0, 0 together, which are the bits of the Alice, what we can do, alpha 0 can be written in this form, simple algebra. Here also you will find another 0, 0 here. You see, if we take 0, 0, you will get beta 1 from here. Similarly, if we take 0, 1, you will get this one, 1, 0 together, 1, 1 together. So the states can be rewritten in this form. Now, since this electrons or the bits were entangled, okay, since we have changed, we have applied something, you see, since it was inseparable, entangled, since we have applied Hadamard gate on the Alice bit, actually Alice applied, the Bob bit is getting disturbed, okay, and it has become something like this, alpha 0 plus beta 1, alpha 1, beta 0, and all this. Now think about what was the intention of Alice. She wanted to send alpha 1 by root 2 alpha 0 plus 1 by root 2 beta 1. That was her intention to send. Maybe, sorry, not 1 by root 2, alpha 0 plus beta 1. Okay. And now Alice is having this part, Bob is having this part. Alice is having this part, Bob is having this part. Something like that. Now, if Alice measure her qubits, measure means it will collapse now. From the wave, it will collapse. So if Alice measure and she gets 0, 0, Bob's bit will automatically be collapsed into alpha 0 plus beta 1. Bob has nothing to do. He is not doing anything. Alice is operating on her qubits. Alice is measuring. Now say if Alice measured her qubit, either she will get 0, 0 or she will get 0, 1 or 1, 0 or 1, 1, because measuring means classical. Now I am using the term or, classical. So whenever Alice will get 0, 0, automatically Bob's bit will be alpha 0 plus beta 1. Now think about what was the intention of Alice. She wanted to send alpha 0 plus beta 1. Now if Alice receives 0, 0, Bob will receive alpha 0 plus beta 1. Maybe he is sitting in moon, okay, on the moon. Now by mathematically I have shown that the data that Alice wanted to share with Bob is being transferred to Bob without having any communication channel. They are separated by maybe light years, okay, right? Now someone may ask that, sir, if Alice get 0, 1, then what will happen? Yes, Bob will get wrong information, alpha 0 plus beta 1, right? That is correct. But information is information, whether it is correct or not incorrect, that is, I will tell later that how it can be corrected. But till now, which was not possible by the classical computing is possible by quantum computing, that at least we can send, we can transfer the information from one point to another point without having any communication channel. Whether it is correct or incorrect, that is immaterial now, up to this, okay? But there is another way. You see, you are having chance of 1/4 time you can receive the correct information, because this is probability. So if we go on experimenting same thing for 4 times, there is a high chance that at least once I will get the correct information, right? So we'll go for experimenting 4 times to get one correct information. We may increase the number of experiments, maybe 40 times, 400 times, 4,000 times, 40,000 times to get the correct information, right? Or there is another way where we can use a little bit of help of classical computing or classical communication system, so that by applying simply 2 bits communication system, we can transfer huge amount of data. So by applying a little bit of classical computing, if you want that always I want to get the correct information, we can do this. Suppose Alice got 00, Bob will do nothing. So how? Now we need a telephone system or any digital system where Alice will say or share that I have received 00. Only she will take up the telephone and say 00. Alice, Bob will not do anything. If Alice say received 01, what Bob will do? He will apply X gate, and you see this 1 will become 0 and 0 will becomes 1. If Alice says 10, Bob will apply Z gate. By applying Z gate, alpha 0 will remain same alpha 0, but minus beta 1 will be plus beta 1. Similarly, if C says that I have received 1, first Bob will apply X gate and then Z gate, and after that Bob will get the correct information. So what we have learned from here, if we repeat the experiment uh, at least for 4 times, there is a probability with 1 to get the correct information without having any communication media. If we want to receive the informations always correct, then we have to establish a communication channel where by sharing only 2 bits of information, classical bits 0001 and 1011, they can share infinite number of information which is inside this state alpha 0 plus beta 1. So which is a tremendous fruitful computing system for quantum computations. So this is teleportation. Some others different algorithms are there like Grover search, but I will not explain all these because already we have reached to the time 7:20. Okay. So by Grover search, we can go for searching an element in the unstructured database by order of root n. I'm not going to this. But nowadays, not only quantum computing, but quantum machine learning is also a very booming subject. Okay. So here you see quantum information processing and machine learning. This quantum machine learning is the intersecting point of these two. Mainly this is used for classification mainly, but nowadays people are also doing the linear regression too by using quantum machine learning. Also you can apply quantum deep learning, you can learn all these, I think, for the throughout your FDP. I think some of the speakers will be there, they will discuss on this. Okay. Type of algorithms for quantum: one is classical computing and classical data. One is classical computing, that is algorithms, but the data are quantum. Or here types of algorithms. So classical data, quantum algorithms. Here the data is quantum, but your algorithm is classical. Here the data is quantum and the algorithm is also quantum. So these are the 4 different types of quantum algorithms nowadays people are using, not the quantum, classical and quantum both. Okay. So here the most popular quantum machine learning algorithms are quantum binary classifier, quantum k-means clustering, quantum SVM. So all these can be discussed or later, or maybe you can search it and you can study it. These are very interesting. Quantum machine learning algorithms are there based on Grover search. Quantum enhanced reinforcement learning is also there. Okay. So these are the future studies that you can do. And how these quantum machine learnings are working, that is also I'm not discussing here because it will take a lot of time. But anyway, these are all possible. So if you have any queries, then I can try to reply.
Yes, we have already posted to the chat box that
Oh,
participants, if you have any queries, you can post through the chat box.
so may I discuss the this PPT sharing mode? Then I will be able to see
Yes,
the.
yes, sir. Yes, sir. No
Okay,
problem, sir.
okay.
Participants, if you have any queries, you can directly ask Professor Changder.
Or my email ID is also there, or
Sir,
phone
if it
number.
is possible, you can put
Later,
it to
later
our
you
chat
can
box.
also contact with me if anyone is interested, or if you have any queries and others. So anytime you can contact me. My phone number and email IDs are with Soma ma'am and others. So you can just request them. And other than this, if you have any queries for the time being, I will try my best to reply.
Sir is ready to reply your queries. Participants, if you have any queries, you can raise.
Anyway, so
So hopefully right
hopefully,
now they don't have any queries, or even in after the FTP is over, we can share all details of Dr. Chongdar. So definitely you may contact him. So thank you, Dr. Chongdar, for such a lucid explanation by simplifying some complex concepts. Really, the past 1.5 hours flew by as we enjoyed your wonderful lecture, sir. Thank
thank
you
you
very
so
much.
much.
Thank you very much, sir. So, participants, may we now move on to our second technical session. Thank you, sir, for
Okay.
attending. Yes, yes, sir.
Thanks to all
Thank
of
you
you.
very much, sir. Okay. So now we will move on to our second technical session, and second technical session of our day 2 FDP. So this will be conducted by Dr. Polishil Sen, madam. Madam, are you there in this group,
Yes, sir.
madam?
Yes, sir.
Okay, okay. So may I now request Dr. Sen, madam, to take over the charge. Thank you,
Yes, sir.
everyone.
Thank you, sir. Thank you, sir.
Thank you.
Good evening,